Okay, so hi everybody. It's really a pleasure to be here for this sixth lecture/tutorial of BIOB20. So today we're going to start with a group activity where you guys will be sent to breakout groups. This is not going to be on record, so I'm going to stop the recording while these classes are happening. And just a quick, just a few information about how this is going to run. So we're going to give it until 5:30 to work on these group problems. During this time, I'll be randomly visiting the rooms just to see how things are going and maybe helping the ones who have the most difficulties. So we'll be working until 5:30. At 5:30, I'll just close the breakout rooms. That will bring us back together, and then we'll have a 5-minute break. We're going to make the 5-minute break between the breakout exercises and the 1.5 continuous remaining time that we have to work on the tutorials. And the tutorials will go as usual with 15 questions. I recommend that while you are in the rooms, start by saying hi, being polite as usual, and explore the topic of giving each other's way to contact each other, like your email or whatever is comfortable for you. But you don't have to, okay? If you don't want to be contacted by the other members of the group, this is of course entirely up to you. But I think that this would be nice if you start by, making this possibility real, so that when the activity is finished, you still have a way to keep in touch with each other in case you want to. So that's what I have to say for the exercises. So they're on Quarkus. If you haven't done so, go to Quarkus, take the quiz, and this will give you the exact problem that you have to solve. So that's it for now. You can go to your breakout rooms and start the exercises. The rooms are labeled 1 to 7. So go to the one that has the number of your group, and you can start now. And here we go, back together for the recording. So I hope you enjoyed somewhat this activity in group. It's a bit normal if in the beginning it's slow to start, like you have spent only 25 minutes together, 20 minutes even. So yeah, like there always needs to be some time to break the ice, etc. And I think that this is important moving forward, that on the next weeks you prepare the problems a little bit, that at least one person or two people in the group would prepare the problems, so that you can kickstart. You have something to say right off the bat. So I really recommend that. I've seen that some groups were ready, they had already thought about a strategy, etc. And some groups were a little bit taken by surprise, and of course there the discussion is much more, the inertia is much higher. So my recommendation really for these activities is come prepared, have some idea of what you're going to do, etc. Bring it to the group and see how they respond, etc. This particular line of problem that we're solving this week is not particularly difficult. It's not particularly easy either. Like, it takes a bit of thinking, but I really want to highlight that this is a very deep problem, in the sense that it will show a lot about how things work. And the hint that I gave offline for those who are watching now the recording is that pretty much the only function you need to solve it is the function d norm, that gives you the probability of the Gaussian distribution. And for now, this is the only hint I'm going to give. I also saw that the rooms were quite imbalanced. Some had much more people than others. So for the rooms, for the people who were in rooms with almost nobody, I'll get in touch with you to see how we can maybe merge you with groups that also had few people, so that we can make bigger groups. I'm a little bit surprised that we have plenty of people who did not attend today, so that made that some groups were not big enough. Okay, so enough about the group activities, and let's start with the activity of the week, which is the gamma distribution and mutations in cancer. So I hope that you guys can see my screen correctly. I think this is pretty much the same as where it is every week for those who are watching online. For the others, yeah, that's of course very different. So let's get started. The problem. In 1971, Alfred Knudsen, a medical doctor at the University of Texas Health Science Center at Houston, published a landmark epidemiological study of retinoblastoma. Retinoblastoma is a rare form of cancer that affects only young children because the tumors emerge during the development of the eye. Knudsen distinguished a familial form of retinoblastoma, where some mutation favors the appearance of multiple tumors in both eyes, okay, and a sporadic form with a single tumor in one eye. So one big one, but in only one eye. It had been proposed that cancer was a multi-step process involving the occurrence of several somatic mutations. Knudsen hypothesized that in the familial form, one of these mutations was already present in the germline. So this work here takes place in the early 90s. People knew, they had already figured out about cancer that this was, in general, in humans, not a contagious disease. That was kind of a pseudogenetic disease. And they had figured out that there were mutations taking place. And so what I mean when I say the soma versus the germline, the soma is all the cells of the body except the gonads, and the gonads is the germline. So basically the soma are the cells that you're going to keep for yourself, that every individual keeps for themselves, and the germline is what they pass on to their children. So these are the two lineages in the body, and overall there is really the stuff that will go forever through the ages, for billions of years, and the cells that will die with you and with whoever you are. So that's the soma versus the germline. Knudsen set out to use the kinetics of the two forms of retinoblastoma to count the number of mutations that are necessary for the initiation of cancer. So that's of course a very important question. If you assume, which seems to be the case, that you need a certain number of mutations to hit the genome, and when you have enough mutations, then the cells will start a cancer. The question is how many mutations are necessary. Are we talking about a mega protection, like 100 mutations before something would give a cancer, or just one mutation would be enough and bang, suddenly the cancer starts? And so that will give you an idea of what's the level of protection from the genome that's given to a person before they start getting cancers. The familial form of retinoblastoma. The familial form of retinoblastoma is typically bilateral, with multiple tumors on each eye. Okay, remember that there are two forms, the one that touches both eyes versus only one eye. And so when it touches both eyes, it's a familial form, which means that in general, when people have it, their children will also have it. But the sporadic type, it's not familial, meaning that when someone has it, it just appears out of nowhere, and the children don't also seem to have it. We will consider that all the bilateral cases of retinoblastoma are due to the familial form. Download the data containing the age of patients in months at the time of diagnosis for bilateral retinoblastoma. So as usual, I'm giving you the URL. Oh. Okay, I got disconnected for a minute. Sorry about this. Yes, Hyder, can you go ahead?
Sorry to interrupt you. Did you is the assignment for this tutorial published on Quarkus? Because
No.
I can't see. Okay.
No, it's not there. I will do this as soon as today's class is over. And so like I explained, I'm running behind a little bit, and just because I was ill, I was not able to do all my usual duties for this week. Sorry about this. I'm going to try and catch up, and in principle from next week we'll be back on track, and you won't have to have this annoying wait that's probably only for this week. So my apologies about this, but it's gonna come right after I'm done with this session.
Thank you.
In general, it takes between 1 and 2 hours for me to create the Quarkus assignment. So I'll hope to do this right after the end of that session. Okay, so I'm not sure exactly. I saw that my internet got disconnected for a minute. I hope it was not too bad. So here we go. There is the OR session. So we're ready to start. And as usual, we paste the URL here that I put on the internet, and we're creating a sample that we call BIL for bilateral, where we read the information from the URL directly. So this is fairly standard. You copy paste the link in your session and you have access there to the data in the variable that's called bil for bilateral. Question 1, run the usual checks for imported data. What is the length of the data set? So what are the usual checks, by the way? Head or tail, dimensions, etc. Absolutely. Okay, so we're going to just say we start with the length. We know it's 23, so it should be 23 here, of course. We can see the head. So in that case, 23, we can show the whole thing in reality. So that's the best way to look at the data when it's relatively small, when it fits on the screen, print it all. That's my recommendation. And then the dimension. In the case of a vector, I did not really mention this, but when you do this, what is the answer? It's no. So dimension only for a matrix, says Mira. Exactly. Okay, a vector has a length, but doesn't have a dimension. And if you say the length of a matrix, it exists, but it's not what you want. What you want is the dimension. So if you're reading a square matrix, a dim. If you're reading a vector, it's length. Of course, you don't know which is which when you just have a URL like this. And this is why there's a bit of trial and error. Like you try one and it says can't read this because, it doesn't look good. So you say maybe it was a matrix after all, then you change the function. You would use read table instead of scan, or vice versa. Anyway, so you see the whole data here. So each number is a patient, and that's the age of the patient in month at the time when the retinoblastoma was first diagnosed. And so you can see that these are, of course, very early ages. So this is a pediatric cancer. It's something that really touches on children. And after 2 or 3 years, like there's really no chance of getting that disease as far as I understand. I'm no physician though, so I won't really, lecture you about this. But this is something that seems to be clear only that children are victim of that. To analyze the kinetics of cancer formation, we need a distribution to model random times. So here we go. Definition 1, the gamma distribution. The gamma distribution is a continuous distribution that models waiting times of consecutive events. The gamma distribution is defined over non-negative numbers and has 2 parameters, known as shape and scale, both positive. The shape parameter is the number of consecutive events that wait for, and the scale parameter is the expected time before an event happens. So you see when you want to model the waiting time, like how long does it take before I have accumulated so many events? Well, you really need 2 things, like how many events do you want to wait for, and also how long does it take for one event to happen. Yeah, there are really many cases that are covered by the gamma distribution, from the number of successes. Like imagine that you have some events that happen over a certain period, like you play the lottery or something like this. Like how long do you have to wait until you win the lottery 3 times in your life, something like that. These are typical questions that can be answered with the gamma distribution. The key points to remember is that the events have to be consecutive. You get one, and then you obtain that event, and then another one starts to count. They cannot occur simultaneously. You can't count the time simultaneously if you're using the gamma distribution. We will not need the formula, but a variable x follows the gamma distribution gamma of alpha beta if and only if that beautiful formula here, which is formula 1, where gamma of alpha is Euler's gamma function defined as this. So this is a little bit the mathematical jargon for those of you who one day, or maybe now, will be interested in looking up the reference. But again, we'll never need that. All we need to do is to be able to sample from the gamma distribution, and this is the function or gamma in or, and to know the probabilities of gamma events, and this is d gamma. So it's always the same thing in or. The function starts with a little or when this is for resample to get some numbers taken from that distribution, and with a little d when is to know the distribution, the probability of that distribution. Knudsen suggested that a single event was necessary for cancer to appear in the familial form of retinoblastoma. We thus need to test whether the data has a gamma distribution with shape parameter equal to 1. Okay, you get this? So when the shape parameter is equal to 1, shape is the number of events to wait for. If it's equal to 1, it means that you just have to wait for one event, and as soon as that event has happened, then bang, cancer starts. So that's what it means. Right? So it means that in the ideas of Knudsen, then this a good model to represent the familial form, the one that has bilateral retinoblastoma, is to say that we need to use the gamma distribution with shape equals 1. So question 2, when the shape parameter is equal to 1, the gamma distribution is the same as the exponential distribution. Suggest a method to check this fact empirically. And the hint is use the function dexp and the function d gamma shape equals 1. So are there any ideas out there for how we could check that indeed the gamma distribution with shape equals 1 is actually the exponential? Ideas? Pass the same number into the two function. Yeah, that's pretty much it. Okay, so we generate a sample from any of these distributions, or pretty much anything possible on Earth, and we're just going to check a couple, but let's say 5 or 6 would be enough. If we always get the same probability with dexp, which gives us the probability for the exponential distribution, and d gamma with shape equals 1, then we say, yeah, like they're pretty much the same distributions. So what would that look like? We just need to create an arbitrary sample. Okay, so I'm going to call something arbitrary here. And for example, what I could say is that I'm going to use the function rexp to say that those are numbers from the exponential distribution, but it doesn't have to. I'm just getting 5 numbers like that, and I'm taking the ones from the exponential distribution. And so now if I want to know the probability of each of them, then I can use the function dexp, okay, of arbitrary here, and that gives me the probability of each of those numbers in the exponential model. So I've took those 5 numbers, but I could have taken anything. All right, so this here is completely arbitrary. I've just chosen that today because this is the mood I'm in, but on another day I would have chosen something else. What matters is that here we have their probabilities as given by the exponential, and let's see what is their probabilities as given by the gamma distribution. So we replace the x by d gamma, but we say shape equals 1. And okay, no surprise, that's what I wanted to check. You can see here that the probability of each of these numbers is exactly the same when you use the function d gamma with shape equals 1 and dexp. So it's not a proof, but empirically we say, okay, we checked it on 5 numbers that were literally could have been anything, then we're quite confident that for any number we look at, these two distributions are going to be the same. So all this to say that the gamma distribution with shape equals 1, when you wait for only one event, then you have an exponential waiting time. Let's move on. In other words, Knudsen claimed that the waiting time for bilateral retinoblastoma has an exponential distribution. That's just translating the claim of Knudsen. For a graphical check, we can sort the values x1 to xn in increasing order and plot them against the series log n divided by n plus 1, n minus 1 divided by n plus 1, etc. until 1 divided by n plus 1. Okay, you have n numbers here, and they're computed always in the same way, which is the k number divided by n plus 1, take the log. The points should be aligned if the sample is drawn from an exponential distribution. So this is a classical trick. When you have an exponential distribution, when you think you have one, you can just plot the sorted values against the log of those values here, and that should give you a straight line. If you get a straight line, then it tells you that indeed the samples are exponential. Otherwise, you get something else like half moon or something like that. So question 3. load the library ggplot2, use it to draw a scatter plot to visualize whether the values of the sample bill are drawn from an exponential distribution, and conclude. So we're going to use ggplot2. So go ahead, load ggplot2. Oh, that is such a problem here. Okay, so obviously I didn't install ggplot2 on the computer, so it's going to be a little bit difficult to show these things right now. So you guys go ahead and oh, thank you thank you, Mark. Getting confused, and indeed I have, thanks God, installed ggplot2 on this computer. So with that, then we need to look at the instructions. First, we need to sort the sample in increasing order. Okay, so we could do something like sorted bill, and that would be sort bill here. Okay, so those are now the numbers that correspond to the age of diagnosis at the time when these young children got the diagnosis with a bilateral retinoblastoma. And I also need to prepare the numbers that be that. So I let you think about it. How can I create these series of numbers that are there, like this log k divided by n plus 1, and you see that n is the number of items in the sample, so that's 23 in that case. So how can I create these series of numbers that are there? Anybody has an idea? Create a function. We could do this indeed. Something faster. There's a way to just make them just like that in just one line. So if we think about it, we have use sec. That's one function we can use there. We can also use, remember, like this notation. Maybe you guys remember it. So that's the number from 1 to 23. Well, it just so happens that you can do the reverse. You can do that, 23 colon 1. And so that's the number from 23 to 1 here. So that's the numerator of the numbers we're looking for. That's here, the n minus 1, etc. What's the denominator? That's 24. So what happens if I do that here? Well, you could see that this looks pretty much all right. So that here gives me the inside of the logs that we get here. And if I want to take the log, well, I just have to wrap it all in a log function here, and I get the numbers. Well, I have to trust that these are the right numbers. It's very hard for me to just know like that the numbers are really the log of these numbers here. And it means that I can just in one go, using that little trick, create the y-axis that we're going to put here. So I'm going to call it, for example, log n, and I'm assigning it to that. Okay, so I've got my x, which is the sorted bill sample. I've got my y, which is the log n terms, and I'm ready to plot these things here. So when we do the normal, when we don't use ggplot2, remember it's just a matter of saying plot, and you'd say x equals, in that case, sorted bill, and y equals log n. Sorry for the typo. Okay, and that gives us here the result, and we can see that they're pretty much in a straight line already, so it's going to be a yes. But we're going to use ggplot2, and so ggplot2 has a relatively different interface for the plots. And so here we go. I will start with ggplot. Okay, the way you start a plot is ggplot, and as you remember, it's got this kind of a little bit complicated way of specifying the data. you need to put here the data frame, and there is this aesthetics that you need to put here. And as we type this, we realize that, yeah, one very strong feature of ggplot2, is that we need to first package things into a data frame. So here we go. We're going to put the two variables, sorted bill and log n, into a data frame. So I call it that because I don't have a lot of imagination, and I don't call it data. I never call my data in OR, and the reason why I don't do that is because data is actually already something in OR. It exists. Okay, so it's something that's fairly complicated here, but if you call something data, you're overwriting that something. So you no longer have access to that in OR, which is why you see that very often I'll be writing that instead of data for my data frames. So this is data frame, data dot frame. That's here like a matrix, except that the columns can have different types. And then we're going to say something like sorted bill equals sorted bill, and log n equals log n. And if I say head of that, you can see that I got two columns, one which is called sorted bill here, and the other one that is called log n. So I'm going to just emphasize this one more time. If I change here this thing, I call it x here and y, you could see that this changes the names of the columns. Okay, so here the first one I'm saying sorted bill is so that this is really the name of the column here, and the second time I say sorted bill, it's so that it references the vector that I just created above. And the same thing here. The first is the name of the column. The second is really what I want to put inside this column. So I go ahead and regenerate this one here with the two column names, which are sorted bill. Oh, let's call it log G. Log n it should be. Okay, so I've got these two things that are the column sorted bill and the column log n. And now I'm finally ready to start the ggplot. So ggplot, then you have to say the first item is that's the data frame where the data has to come from. And AES stands for aesthetics. And so the aesthetics is going to say what are you going to plot in this data here. All the data is going to come from there, but what are you going to plot? And so we need to say that the x-axis here of my beautiful plot is going to be sorted bill, and here I'm referring to the column in that, and y is going to be log n, and I'm again referring to the column there. Okay, so I can do that, but that doesn't really do anything. I need one more thing, which is a geometry. And for the scatter plot, does anyone know or remember what is the geometry that is required to make the scatter plot with ggplot? Geom point. That's good. Excellent. And when I have this, well, you could see that I get the plot. It's pretty much the same information as the other plot, but it looks a little bit more, let's say it's got more taste. ggplot2 is a replacement of the OR graphical functions, but they have been made by a graphical designer. So I think that's the PhD thesis of a student in statistics and graphical design. And so they have completely re-implemented all the basic features of OR. So it's the same. Basically, you can do pretty much every figure you can make with either OR, the normal OR, or with ggplot2, but the way that the interface works is completely different. And the default of ggplot2 are much nicer looking than the defaults of OR. So one thing is that the standard way that ggplot2 plots things is that it puts this gray background and a grid which has white lines that you can see there. So this is considered most designers, most people who work in data visualization, etc., say that this is a bad thing, like graphically, because it takes way too much attention on this background here. Whenever you plot some data for people to analyze, you want to draw their attention on the data, not on the background, not on the axes. You want them to see what's going on with the data. So that's considered, many people consider it bad practice. And yet, I've heard, I'm not sure it's entirely true, the designer of ggplot2 has decided that this would be the default because they assume that it would be mostly data that is used for projection, and on many projectors the quality of the light is not very good, and that does emphasize the contrast quite a bit. So when you print something on a paper, I really don't recommend using the defaults of ggplot2, but when you show them on a screen like we're doing now, they're pretty good. So there is a way to change a little bit the outlook, and so there is what is called the theme, and that's what I'm showing in the video. You can use the theme classic instead. And so the theme classic, you can see, has much less which is printed on it, and that's a better format for paper. But when you're using the screen, it's fine. Like you can use the default of ggplot2. It's actually quite nice when you're on the screen. So conclusion. Well, obviously the points are aligned. Okay, there's a pretty nice line that is here, so it seems okay to think that these points are indeed taken from an exponential distribution. Question 3. Load the it's done already. Knutson's argument suggests what is the lowest graduation on the y-axis? It's -3 here. Knutson's argument suggests that shape equals 1, but we still need to estimate the scale parameter of the distribution. We will do this with the maximum likelihood method. So today is again about the maximum likelihood. So here, remember that the gamma distribution has got two parameters. There's the shape parameter and there's the scale parameter. So if we say, okay, fine, shape equals 1 seems okay, in the sense that it just means that the distribution is exponential, and it does look exponential, that's fine. But what about scale? So before we do that, let's remember what scale is. So question 4. The parameter scale of the gamma distribution is the average time for one event to occur. Okay, so like we have events that are in month, and now we need to kind of scale the time in terms of month, so that the data that we observe is at least in the right unit. You know, these are months, these are not seconds or minutes. Based on this information, what is a good guess for the maximum likelihood estimate of scale when shape equals 1? Does anyone have an idea? Okay, you get the question. So if scale is the average time it takes for one event to occur, and we know that with our assumption there is exactly one event that occurs before cancer, maybe 12. I'm not sure why why you said 12. Was there a reason why you said 12, Marco? I guess the reason is more interesting than the actual result. So let me go back to where I was. So if scale is the average time it takes for one event to occur, and we assume that cancer happens after one event, okay, well, maybe we could say that actually a good guess for scale would be the average of the sample. That actually makes sense when you think about it. Because the average of the sample has to be the average time it takes for one event to occur, right? If we assume that one event occurs, now we're working with that assumption, then the average of the sample has to be the average time for one event to occur. Does that make sense for everybody? Okay, like it's a little bit complicated before you think about it, but after you thought about it, it's actually kind of obvious. So scale is the average time it takes for one tumor to appear. If shape equals 1, right? Because we're saying that we assume that shape equals 1, which means we assume that it takes one event for the cancer to occur, at least in this case, in the case of the bilateral familial form. In that case, yeah, the average of the time it takes for the cancer to occur is the average time for one event to happen, because we have made that assumption. But when we will make the assumption that shape is different from 1, it will no longer be true. Okay, but for now, we could say that like we have the mean of the sample, that's 14.47826. That's probably a good guess for what is the maximum likelihood value for scale when shape equals 1. Okay, I repeat, when shape equals 1, we have one event before cancer happens. So the time it takes for cancer to happen is indeed the time it takes for that one event to happen. Okay, so here that's going to be our guess. So we say guess is the mean of the sample. I hope that makes sense for everybody. If not, just stop me, write in the chat, and I can explain that again. But again, I insist, it's only because shape equals 1 that this holds. Question 5. Using the maximum likelihood method, show that the guess of question 4 is actually the maximum likelihood estimate of scale. Oh wow, pretty cool. Then we're kind of done with this long process that took us hours last time we did it. So that'd be nice. Would it be the case that 14.47826 is the maximum likelihood estimate? Well, that'd be pretty nice. And this is indeed the case here. Okay, so how do we work the maximum likelihood estimate? Well, it's always the same story. First, we need to get the individual probability of occurrence of every event in the sample. And this is done by the function d gamma. Okay, it's not always d gamma, of course, but we have assumed that we're working with a gamma distribution. And the d here, that's just there, just tells us, give me the probability of observing these particular events. So that's here, d gamma computes that for us. That's exactly what d gamma does without bothering us with the details. So we want d gamma, and we want the value of the gamma distribution, the probability of the gamma distribution for every element in the sample. Good, but we need to give the parameters. So the first is easy, shape equals 1. It's fine. And then the second is also easy, we just made a guess. So scale equals guess. And if I press enter here, I have the individual probability of occurrence of every element here in the sample bill. Okay, so these are not very high probabilities, but who cares? Now, what is the probability of observing them all together? These are independent events. Therefore, the probability of observing all those 23 values in that order is the product. And remember, like, prod is the product function. So here, that tiny number which is here is the probability of observing all those 23 numbers if scale is equal to guess. But that's, we made plenty of assumptions here, okay? We made the first assumption that this is a gamma distribution, second assumption that shape equals 1, and third assumption that scale is that guess that we have. So that gives us that particular probability of occurrence. Fine. Now how would we show, how would we at least empirically demonstrate that the probability cannot be higher than that, that the likelihood cannot be higher than that? When I'm going to change scale here, it's going to go lower. It can never go higher. Well, quite simple. I'm going to see what happens if I change scale just a little bit. I remove just a bit from my guess, minus 0.1 for instance, and I get a number here which is just a bit below this one. Okay, you guys see this? This is of course a very small number, minus 37 here. This one is 0.64 and this one is 0.63. So it's slightly lower. I hope you guys see that. Okay, so if I change my guess by making it a tiny bit lower, then I've got a lower probability. What happens if I make my guess a tiny bit higher? Well, again, I get something that's lower than when I have the guess here. That was 2.064 and now that's 2.063. So no matter where I go, tiny bit on the left, tiny bit on the right, it seems that I'm losing likelihood compared to the original value of guess here. So that's good enough a reason to say that guess was already the best number. You know, you can't change it. If you change it a little bit, add or remove, both times you go down. That was already the highest value here. So that's a bit of an empirical way to demonstrate that this guess, which is just based on the mean, was actually more than a good guess. It was the absolute most excellent guess because that was already the maximum likelihood estimate. That's something that's fairly standard in maximum likelihood estimation, is that very often those estimates are the mean or, you know, sometimes the median, etc. So these are, you know, the mean and median are good estimators for a reason, is because they're often the maximum likelihood estimator. I hope it works for everybody. I'm going to redo it one more time, this time using the log likelihood. Okay, so this here was the rational using the likelihood, but there is another way to do this, which is using the log likelihood. It's just to say that because the probability or the log of the probability are kind of on different scales, of course, but still, if you maximize the probability, you will also maximize the log of the probability. And these tiny numbers here that we see will not risk to underflow, that my computer doesn't have enough bits to represent these values. Here we're kind of far from it, but you can see that we have only 23 values in this sample, and this is already 10 to the minus 37, a very tiny number. So in general, we don't do what I just did. We compute all that in log space. So which means that we're not computing the likelihood, but the log of the likelihood, which looks like that. So it's going to be that number here. And the first way to compute it, which is the bad way, and that's the way I'm doing right now, is to say compute the likelihood and then take the log. But that's a horrible idea, because that can underflow and you can actually have already an error at the moment when you take the log. What you have to do instead is to go back to the probability distribution here and say that you want the numbers already in log. So those numbers that you see here are the log of those numbers that you see there. Okay, you have computed them individually in log space, and some are extremely unlikely, for example -5 that you can see here. Some are kind of not so unlikely, like -2. And now if I want to compute the log likelihood of the whole sample, remember that I have to take the sum, and that's because the sum of a couple of logarithms is the logarithms of their product. And you can see that here I of course get the same number. Okay, because these are equivalent and I did not underflow, so therefore this method here above actually worked. However, when the samples will go bigger, the method here will fail and this one will succeed. So we're going to stick to this one. So that's the log likelihood when the scale is equal to guess. And now what happens if I change guess by making it a tiny bit lower? Well, this number is actually lower than this one. Okay, this is in the negative space here, so always a bit annoying, but that's a lower number than this one. And if I now increase my guess by just a bit, again, I get a number that's lower than this one. So that's my record. That's the highest value I can reach here. Okay, I've done it 2 times. I think that's enough. Most of you will have gotten the points. This is something that we have seen before. We've drawn the whole curve, if you remember, in one of the previous chapters. And so here, with this trick of taking the mean, I can already directly go to the top of the curve. Like I know already that I have the point which is on top of the curve, which of course means that when I'm going to go left or right, it's going to go down. My estimate here, when scale equals guess, was already the best. So let's move on. Using the library ggplot2, add to the scatter plot of question 3 a line with slope -1 over s, where s is the maximum likelihood estimate of the scale parameter. Okay, so here this is a question which is just to add a line to a plot using ggplot. And so in OR, remember, there was the function AB line. That's the one that really puts a line on the plot, and AB stands for the parameters in the Cartesian coordinates like A and B. And in ggplot, there's this function which is called geom AB line. So we can take the here the call for the plot again, and the way we add a line on ggplot is geom underscore AB line. Okay, and here we have 2 parameters like intercept and slope. So I say intercept equals, I want it to go through the point here 0, 0. So that's 0. And here slope, what do I write? I'm listening. Suggestion based on what is requested. I remind you, we want to add a slope -1 over s. So what do I write here? In other words, what was s? The maximum likelihood estimate of the scale. Minus 14.47, almost. So the maximum likelihood estimate is the mean of Bill, so that was 14.47, but I want a slope which is -1 over that. And you can see that it draws the slope here at the which really goes more or less how we expect it. Of course, these points here are out of the trend, as we can see here, but that really tells us that we got it right. Like this estimate that we had is indeed correct. This 14.47, taking the mean of Bill, is really the best idea that we can have to estimate the scale parameter. So that kind of tells us we did a good job with that estimation. Let us now investigate how solid Knutson's assumption was. We will examine how shape equals 1 compares with other values. So far we went along with the narrative of Knudsen. We say fine, like Knudsen says shape equals 1 is really a very good model for this bilateral retinoblastoma, and we said yeah, sure, it looks like it here, fine, but we still need to test other values. What about shape equals 2? Maybe they will be even better in catching these points here, etc. So just because we have one good guess doesn't mean that our job here is done and that we have to stop. So we have to still test other things. So question 7, set shape equals 2 and use the logic of question 4 and 5 to find the maximum likelihood estimate of scale. So here we go. Now we say shape equals 2, and remember, so here when I use this guess here, it was based on the idea that shape equals 1. But when I put 2 here, and the guess, remember, was the mean of the sample, when I put shape equals 2, I won't be able to make that guess anymore. But if I think a little bit, I think maybe I'll be able to get out of this. Let's roll back. Shape equals 2 means that we now believe that in order for the cancers to happen, 2 events have to happen. Okay, like 2 mutations, 2 consecutive events have to happen. So you need to have the whole time for the first event plus the whole time for the second event. And the sum for these 2 events here, that is the new time that is required for the cancer to happen. So based on what we said before, it kind of seems logical that a good estimate that we can have is the mean of Bill here, well, divided by 2. Okay, so think about it. If the total time it takes before cancer appears is 14.4 months, and that this is the time for 2 events, wouldn't you agree that each event takes about 7 months, 7.2 months actually? So that's all we're saying here. We say if you need 2 events for this to happen, and the average is 14, then the average of an event has to be 7. It's as simple as that. So we could use that. We could use the fact that now when shape equals 2, the guess would be the mean time to cancer divided by 2, because that's the contribution of 2 events, not just 1 anymore. And so that will give us this. I will just say a guess, new guess, is the mean of Bill divided by 2. So now that's my guess here. And again, I can take the product, and that will give me here the likelihood when shape equals 2 and scale is equal to my guess. And we're going to check that this guess is indeed, once again, the maximum likelihood estimate. We do the same trick. We say, what about I change the guess just a little bit? So it goes from 639 to 631, that's lower. And when I increase it just a little bit, it goes from 639 to 632. That's again lower. So that was indeed the best here, the best estimate that I could give for shape equals 2. So that logic that we used before, it works again, and that's very happy here. So the mean of Bill divided by 2 is already the maximum likelihood estimate when shape equals 2. So use the logic of questions 4 and 5 to find the maximum likelihood estimate of scale. So that's it. In this case, the maximum likelihood is 7.23, and that's just the half of 14.47. So far so good. Is that okay? If you want me to repeat that, just say something in the chat or ask a question, and I'll answer that. Question 8. Compare the maximum likelihood at shape equals 1 and shape equals 2. Which value is more plausible? So here the likelihood for guess was 1.6, let's say around 6.4 to the minus 37. And previously, with in the previous case, when shape equals 1, we had seen that this was 2.06, 10 to the minus 37. So those are the two values here. I'm going to try and give a little bit more space on my screen, but it doesn't help much. They're too far apart. So one of them is, well, no, they're not too far apart. One of them is 1.63, 10 to the minus 37. The other one is 2, 10 to the minus 37. So you can see that there is something like a 50% increase. That value here is 50% bigger than this one, which means that when you say shape equals 1, you can get to a higher level than when you say shape equals 2. Here, that's the maximum you can get when you say shape equals 2. I hope you see this, that once you've set shape equals 2, there's no way that you can make scale such that you can overshoot that value. That's the max of the curve here. And with shape equals 1, there's another curve, but it goes a bit higher than that curve. Not a lot, but doesn't matter, it's still higher. So that value here is more likely than this value here. If you say shape equals 1, you can go to a higher level of likelihood or log likelihood. So I'm going to quickly show it with a log likelihood, but it's pretty much the same. So here you say log equals true. You get these values in log here, and instead of computing the product, you compute the sum, and that gives you minus 84.70, and that is already the maximum likelihood estimate, and this is the maximum log likelihood. So we have to compare minus 84.70142 to this number here, and this number is higher than this one. Always confusing with a minus sign. So which value is more plausible? Shape equals 1. On this one, it really looks like we agree with Knudsen. This is a good model, like this idea that you have an exponential decay and that only one event, one mutation is required in the familial form. It's pretty solid. I hope you guys agree. Now, what about the sporadic form of retinoblastoma? The sporadic form of retinoblastoma is exclusively unilateral, with a tumor in only one eye. We will consider that all the unilateral cases of retinoblastoma are due to the sporadic form, even though this is not entirely accurate. There are a couple of cases of unilateral retinoblastoma which are actually the familial form. But Knudsen ignores it, so we will ignore it too. Download the data containing the age of patients in month at the time of diagnosis for a unilateral retinoblastoma. So same story here. So we paste the URL and we create the sample that is called UNIL for unilateral, and here we go. Run the usual checks for imported data. What is the length of the data set? So usual things you could do, like the head of UNIL. Here we want to do the length, and that's of course 25, and because it's kind of small, well, we can show it in full. That's as much information as we can get by just showing everything. And already you could see that the numbers are a bit higher here. If you compare them to Bill, there were plenty of numbers that were less than 10, which is super obvious because then there's only one digit. But here, there's kind of much fewer. There's an 8 here, an 8 there, but most of the numbers are obviously visibly higher than with the bilateral case. So question 9 is easy. Knudsen observed that unilateral retinoblastoma occurred somewhat later than the bilateral form, in line with his hypothesis that one of the mutations of the sporadic form is already present in the germline for the familial form. So when Knudsen saw that, his line of reasoning was that, okay, how can it be that the unilateral case, which touches only one eye and gives usually a big tumor, would come out later than the bilateral case, which is a familial form, like the sporadic form. Someone is affected, but their children or their parents don't have it, so it seems that this is something that has happened spontaneously in the soma of the baby, but has nothing to do with the germline. So his line of reasoning was that, it's quite simple. Like, you need, let's say, X mutations for the cancer to happen, and in the familial form, you need X minus 1, because 1 has already been present in the germline. So the germline is already hit with one of the mutations. Therefore, in the familial form, because you need fewer mutations for the cancer to develop, then of course it develops faster. Okay, you guys see the idea of Knudsen is that with his model where one of the mutation is already present in the germline, out of the whatever is the number that was needed, one is present already in the germline, then of course in the familial case it's going to occur earlier than in the sporadic case, because the sporadic case you have to wait for one extra mutation before retinoblastoma can occur. Question 10. Use the strategy of question 3 to visualize whether the values of the sample UNIL are drawn from an exponential distribution and conclude. So it means that we're again going to use ggplot2, So that's the same thing. And we have to remember, sort the elements of the sample here, unilateral, and to do the log trick that we did before. So when we look at the value of n, it was 23 in the previous sample, and this time it's 25. So we will have to regenerate the numbers that were there, these ones. This time n is no longer 23, it's 25. So here we go. We start by creating sorted unil, and that is the sorted values here of the new sample from 8 to 73. And we also have the values of log n, and remember this is 25(1) divided by 26, and we take the log of that. We get those values here. So now if we're about to use ggplot2, we again need to put everything in a data frame as before. So I'm using my good old data frame. So that's the data frame that contains, again, sorted unil is the name of the column, and I want it to be here the vector that I just defined, and the other column is called log n, and I want it to be again the vector I just defined. So now I've got something that looks like this, a data frame with sorted unil here and log n, which is there. And this time I don't have 23 values anymore, I got 25. So I'm ready to call again the ggplot here. So I don't need the geom AB line. This part is not needed. So I'm regenerating here ggplot, that's my data frame which is there. A yes for the aesthetics, it's not sorted bill, this is sorted unil. That's the name of the column here. And the name of this column is here log n, geom point. Here we go. So what do you guys think? Are they on a straight line? Well, I think obviously not. Okay, like it has a shape like that. So it's clear that there's not a single line that will manage to go through all these points here. We also have a pretty strong outlier here, which is very far from the second highest. So this data is going to be a little bit more difficult to work with. It's not going to be as friendly for the analyst as the previous one. So drawn from an exponential distribution and conclude, no, this is not drawn from an exponential distribution. This is extremely unlikely. How do we create lines of best fit in OR? We could spend a whole semester on that question, not just the whole class. So it really depends what you mean by best fit. What we will see at some point in this semester are going to be lines, like straight lines, and we're going to see how to create them. It's fairly easy in R, and so we will see the detail of how that works. But now if you mean non-straight lines, like smooth lines, then this is a whole different story. But I'm going to show you how to do it right now. So when you have the standard plot, you'd say sorted unil here for the x, and you say y equals log n. So it's the same plot again, but more ugly and all. And you have a function which is called lm for linear model. And if you say log n, which is your y value, and this little tilde here, sorted unil, it means try to predict log n based on sorted unil. Then that gives you a whole thing with an intercept and a slope. And OR is kind of friendly in the sense that it allows you to just package this into AB line, and so that's the way you would do it. Fairly simple, OR is fairly friendly, but the problem is that this is an ugly plot. You would have to use some other functions in ggplot too if you want to do that. So there are many ways to compute these lines, and that's the standard way to do it in R. But as you can see here, you know, this is not really going through the points, not at all. So question 11, set shape equals 2 and find the maximum likelihood estimate of the parameter scale for the sample unil. Okay, fine. So we're not going to waste our time setting shape equals 1. Why? Because shape equals 1 means the data is exponential. We have just showed that the data is not exponential. Like this is not a straight line at all. So there's not going to be a very good fit for shape equals 1. So we go directly to the next level, which is shape equals 2. And here we go. So set shape equals 2 and find the maximum likelihood estimate for the parameter scale for the sample unil. So again, how does that work? We have to go back to always finding here the probability of every element in the sample. So the sample is not Bill, it's unil. Okay, and here we're going to just do it like that. So shape equals 2, that's what we need, and scale equals what? The guess is the previous guess. It's not going to be a very good guess because it was the guess based on Bill, and we don't need this data anymore. So whatever was the idea that we had before, it still works. Okay, so if we say we take the mean of the sample and we divide it by 2, that should still be the maximum likelihood estimate. So with this function here, we're able to compute the probabilities, the individual probabilities of every item that we observe. And again, we want the probability of the whole sample. For this, we need to take the product. And we can do that because these are assumed to be independent. So that's it. That's here the likelihood, not the log likelihood, for shape equals 2 at our guess. And we're going to check again that this is the right guess, but there's no reason why it should not be anymore, because so is the same rational, it always works. It doesn't work only with one sample but not with the next. Still, let's show it just to be sure. So if I move this guess a little bit by taking something slightly lower, doesn't look right. Okay, sorry about this. So that is here the potentially maximum likelihood value. If I remove my guess, just a little bit something from my guess, yeah, 2.13 is lower than 2.14, so the likelihood has decreased. And if I increase by just a bit, then again 13 is lower than 14, so on the other side also decrease. So the shape is really like this. That value here, mean of the sample divided by 2, is again the maximum likelihood estimate. So the answer would be mean unit divided by 2, that's 15.92 is my best guess for the value of scale. One shape equals 2. Okay, only one shape equals 2. So Knudsen argued that the kinetics of unilateral retinoblastoma were compatible with 2 events, meaning that tumors would start growing after 2 mutations. We will test how robust this view is. So, okay, we've got the maximum likelihood estimate. We kind of discard shape equals 1 already because the plot doesn't look any reasonable. So, okay, fine. It's going to be probably shape equals 2 then. But we need to check. So let's see. Question 12. Increase the value of shape. Find the maximum likelihood estimate of the parameter scale for every value and store the log likelihood. Which value of shape has the highest log likelihood overall? So now what the question asks is we're going to do something like shape equals 3 here. And so how am I going to find the maximum likelihood estimate? I'm listening to suggestions. If I want to find here the maximum likelihood estimate of the scale parameter when shape equals 3, what am I going to do? Set the scale to mean divided by 3. That's an excellent idea. I hope that everyone agrees. So it's the same rationale. When we had shape equals 1, the mean of the sample was the mean of one event. When we had shape equals 2, the mean of the sample is the mean of 2 events. So if we want to have the mean of each individual event, we have to divide the mean of the sample by 2. And now if we have 3 events, well then the mean of the sample is the mean of 3 events. You know, it's exactly the same rationale. And therefore, to know the mean of one event, we have to take the overall mean and divide it by 3. As simple as that. So we would do that. The product d gamma equals of x is the sample of unilateral retinoblastoma, shape equals 3, and scale equals mean of the sample divided by 3. That's my guess here. And I forgot a bracket. So when we have shape equals 3, it tells us that the maximum likelihood would be that. And I'm going to compute this now in log likelihood. Okay? Just to make it a habit. And I insist is because that always works. And computing the likelihood does not always work, because at some point the numbers become too small and your computer gives up. So here, when shape equals 3, I get that log likelihood. And when shape equals 2, I got that. So which of the two is the winner so far? Is it shape equals 2 or shape equals 3? Well, which of the two values is higher? Is it minus 103 or minus 105? Well, the higher value is this one. Okay, minus 103 is above minus 105. So, surprise, surprise, that here with 3 events is actually more likely than with 2 events. So let's see. Maybe when we say shape equals 4, it's going to be even more likely, or shape equals 5 or 6 or something like that. So now I think the logic is clear for everybody. If I put shape equals 4 here, there are 4 events in the sample, so therefore the average of the time to tumor is the average of 4 events, so we need to divide the mean by 4. That's kind of acquired by now. 102. Which of these 3 values is the one with highest likelihood? Well, it's this one here with minus 102 is higher than minus 103. Okay, is that clear for everybody? That actually 4 events is even more likely than 3 events for that particular data set. So we keep going, we keep rising. So if I'm putting shape equals 5 here, I think everybody will now be comfortable that I divide this by 5 and I get 102 minus 102.997. So is this higher than shape equals 4? No. Okay, this is lower. So we have increased, like 2, 3, 4 was the maximum. 5 we start to decrease already. That here is already lower than that. So let's make sure that when we go to 6 and 7, this still goes down. So shape equals 6. So 6 events to cancer. Yeah, it starts to go down now. And 7 events to cancer. Then, well, it keeps going down. So it seems that when we compute the overall maximum likelihood, we get something that increases till 4 and then decreases. So the winner is this one here. It's this value with minus 102 as the maximum log likelihood. So contrary to what Knudsen said in his paper, it seems that when we look at this data, that the value with 4 events seems to be more plausible than the value with two 2 events. So which value of shape has the highest likelihood? It's 4. That's the answer. It's this one. Okay, the overall best likelihood is reach 4, shape equals 4. Does that work for everybody? Do you guys want me to repeat that, or you could follow the rationale? The fact that we are trying the shape from, well, we're not even trying 1 because this is a no-go. It's obviously not going to be a good fit. Anyway, we don't need to. We've seen that from 2 anyway it increases. So we try 2, 3, 4, 5, 6, 7, and every time, because now we have this neat trick to find the best value of scale, then we can always instantly get the maximum likelihood estimate just this way here, by dividing the mean by the value of shape. And we find that, unlike what Milton said, 4 events seems to be more likely. An outlier is present in this sample. The highest value is 40% higher than the second highest. We still have the ugly plot here, and you can see that, yeah, there's an outlier, it's there. Like the highest value above 70 is kind of way above everything else. Like the second is around 50, and this one is already 73. So that's more than a full year after the second value, which is there. So that would qualify as an outlier. The highest value is 40% higher than the second highest. This point does not appear on the figures of Knudsen in reference 2, so it is unclear if it was taken into account. So okay, we say that there are 4 events based on this data before you get cancer. Knudsen says 2, but when he plots this figure here, it's cut. You know, the y-axis is cut so that you don't really see this point. So do we find a difference because he threw the outlier away? That's something that's fairly common, throwing outliers away. When you have a point like this, my recommendation is don't throw it away just because it looks weird. Analyze it just the way we did, but also analyze your data without it. And you're going to have 2 situations. Either your data is going to change a lot, or your conclusions, not your data. Your conclusions are going to change a lot. So what does it mean if they change a lot? It means that this single point here has a huge influence on your rationale. And in that case, you have to be very careful, because it means that you're going to make a decision which is solely based on one point, whether this point is real or not. Second thing that can happen is that your conclusions don't change. In that case, you're good. It means that this point actually had almost no influence on the results. You can leave it, because anyway it didn't have a strong influence, and you know that your protocol, your data, is kind of robust in the sense that with or without this point, your conclusion does not change because you have enough information with the rest of the data set. So that's my recommendation here. When you have an outlier, keep it, but also run the analyses without the outlier. So this point, whether it was taken into account, we don't know what Knudsen did. It doesn't really tell us exactly what he did with outliers. We suppose he did not remove them because it doesn't mention it, but who knows. It would be interesting to see how influential that single number was for our conclusion. So question 13, create a sample UNIL underscore where the outlier is removed. What is the average of UNIL underscore? So the burden of the question here is to say that we want to create something here which is basically the same as UNIL but without the outlier. So I'm listening for your suggestions. How can I remove the outlier here? In practice, like using OR commands, how would you solve that problem? Here we have 25 values, so we can always create a new sample that's like that. UNIL underscore, you know, that BC, okay, 48, 22, 33, etc. But it's not a very good idea. I'm going to make a typo at some point. I'm going to remove a number, maybe 2 instead of 1, etc. So I'd like to have something that's more automatic. How would you guys do it? So what I want to remove, of course, is the maximum. I want to find which value of UNIL has a maximum and remove that value from the vector. Use square brackets UNIL less than 73, that's an excellent suggestion. Okay, you gotta remember that we can select different elements using this less than or greater than. So I can say unil such all the values of unil such that unil is less than 73. So when I do this, that gives me here a vector where that value here has been popped out. You see this? There are other ways. So this one is a good one, but it requires knowing that the max is this here. So you could also do it with less than max unil. Oh, so that's the same thing. Another function which is really interesting for this kind of stuff is which.max or argmax. So if you say which max unil, it tells you that it's 14, but 14 is not the value that is the maximum. It's obvious, you know, you have 48, 22, they're above 14. Is that unil at position 14 is 73. That's the position of the max here. So if we know that position, we can kill it. So another way to do this is to say unil, and remember this minus notation. We don't use it very often, but sometimes it's very useful here. So minus 14, that gives us the right sample here. So my solution to that question is to say unil underscore is unil minus which max unil. So that's here a way of removing the maximum element from a vector, and that creates here the desired result. And the mean of unil, you can compute this yourself, it's not very difficult. That's here for Quarkus. So Dana is asking, is there a built-in function that removes a specific value from an OR vector? I tried looking it up but didn't find anything. It depends what you mean by removing a specific value. So if you have let's say if you have integer values, like it's pretty clear because you have 1, 2, 3, 4, etc. You can find all the values which are equal to 7 and remove them. But when you have like real numbers like 1.3759, equality is not even guaranteed anymore. Like you have to give tolerance to say these two numbers are equal or not equal. So this question does not even make a lot of sense when the numbers are not integers. But when they are integers, it's very simple. You can use basically the same logic as was proposed here by Marco. So if you want to remove all the values of unil that are equal to 32, you say unil such that unil is not equal to 32. Okay, so now you had 32s before, 132. The number 8 is repeated 2 times, going to be more interesting. So you say that, and you can see that the number 8 is gone. So this here is, remember, a true-false vector, and whenever it says false here, so there's a false here and a false here, it means that this condition is false, and this number is not going to be incorporated in the result. So that is a fairly generic way to remove one particular value from a vector, one target value. You can do more than this. If you have more than one target value, you could say unil in a certain number of values you don't like. I don't like 8, I don't like 32, I don't like 28. And so here that will give you only the ones that are in these values, but you could say not using this exclamation mark here, and that will remove all the values that are in 8, 32, 28. So these are so standard constructs here in R that they're actually difficult to find, you're right, because you don't even know what they will look like, whether there's going to be a real function, etc. And so a Stack Overflow may kind of have a hit for your question, or maybe not. You never know that. Anyway, so that's something that's fairly typical in R, this kind of writing here. So create a sample unil underscore where the outlier is removed, what is the average of unil, and then question 14, find the value of shape with maximum log likelihood on the sample unil underscore. And now time has run out, so we won't be able to do it. But when you're at home and you do this, you will see, using the same logic as the one we've developed right here, whether the problem is just the outlier. Okay, like when you remove the outlier, is it the case that now we find shape equals 2 is the dominant, like the most likely event, and that would explain that indeed what Knudsen did is that he removed the outlier, or are we going to remain with 4, maybe 3, or another number? And in that case, the mystery will kind of be as to why do we see the different results compared to what Knudsen did. So that's as far as we could go today. Thank you very much for being here. I will fill the Quarkus within a couple of hours. So sorry about this. I apologize once more. Please be a little bit more patient, and then I will open the Quarkus quiz. See you soon. See you next week. Good luck with the quiz.